Hello, calculus fans. So we're going to start talking about the fundamental theorem of calculus, but this time for line integrals. And of course, the fundamental theorem that we studied first in calculus 1 is a very important theorem, and this one will end up being similarly important, at least in the context of line integrals. Before we do so, we need to introduce a little bit of terminology and show an important theorem. So the first bit of terminology we want is the notion of what it means for a field to be conservative. And we're going to say that a vector field is conservative if there is a scalar field little f for which big F is equal to the gradient of little f. That little f is going to be called a potential function for big F. The property of being conservative is going to be really useful later when we want to evaluate certain line integrals. We'll show that if we want to evaluate line integrals of conservative vector fields, that there is a very nice shortcut. Be lazy. Our first order of business is to find out a way to check to see if a vector function is conservative. If it is, we also need to be able to compute a potential function. All right, let's run through this example. So I'm giving you a vector field. So its components are yz, xz, and xy plus 2z. Let's find out whether or not this is conservative. And if it is, let's find a potential function. So I want to be optimistic. So when we're going to be optimistic, let's go ahead and just try to find a potential function first. Now, if there is a potential function f, then we know that the partial derivative of f with respect to x will be yz, the derivative with respect to y will be xz, and the derivative with respect to z will be xy plus 2z. So we should be thinking of f as sort of an antiderivative of big F. Now let's go ahead and compute some antiderivatives, and here's what we see. We can compute antiderivatives in three different ways with respect to x, y, and z. So now let's think about what happens when we take an antiderivative with respect to z. We notice that we'll get xyz. Now ordinarily when we compute an antiderivative, we'll say something like, well, we have a plus c. But in this case, sort of like the opposite of a partial derivative, this is a partial antiderivative. So what's out here, this expression, is going to be some arbitrary function of y and z. And then the same thing down here where we compute an antiderivative with respect to y, we'll get xyz plus some arbitrary function of x and z. And finally, if we compute an antiderivative with respect to z, we'll get xyz plus z squared, and now we'll have some arbitrary function of x and y. So we can combine all these, and what we'll see is that xyz plus z squared works as a potential function. Now you can check this. Take the thing that we got here and compute a gradient, and you'll see it's exactly the vector field that we're interested in. And since we have found a potential function, that means that this vector field is in fact conservative. Okay, that's all for now.